Enriched uranium, one of man's most valuable resources. This enriched uranium button weighs 5 kilograms, 11 pounds. Its value, $55,000. These buttons will be alloyed, cast, rolled, or machined to make the various forms and shapes useful to industry, science, and defense. Because enriched uranium is worth almost 10 times its weight in gold, the many forms of salvage and waste products will be recycled again and again to recover the last salvageable quantity of enriched uranium. Throughout these operations, certain basic principles of nuclear safety will be followed to prevent accidents caused by the phenomenon called criticality. Today, most people find no strangeness in our concept that all matter is made up of atoms. Natural uranium is a mixture of two kinds of metallic atoms, uranium-238 and uranium-235. Most of these atoms are relatively stable uranium-238, or more simply, U-238. Only one of every 140 natural uranium atoms is of the more excitable U-235. Both metals look the same. In fact, they can't be chemically separated. Now, if one of the tiny wandering particles that we call neutrons happens to collide with an atom of U-238, it may simply bounce off, or it may be captured or absorbed into the atom. If, on the other hand, the neutron happens to hit a U-235 atom, it may split or fission the atom into several fragments. Part of the fissioning atom turns into pure energy, most of it appearing as heat or in the form of powerful X-rays. In this release of energy, atomic power is born. The leftover pieces of the broken atom are called fission products. They are intensely radioactive and are now entirely different elements of lighter weight, no longer uranium of any kind. A very important part of the fission process is that the breaking atom throws out 2 or 3 of its own neutrons, each of which may in turn hit and fission still another atom of U-235. Thus, we may obtain a constantly increasing number of fissions, a self-sustaining chain reaction, criticality. We can put criticality to work in a nuclear reactor. Excess neutrons not required to maintain criticality may be directed at special targets and, if captured, transform them into radioisotopes, used in medicine, agriculture, industry, and many types of research. Heat emitted during a chain reaction can be used to generate electricity to power large cities, desalt the seas, or power submarines. There is another side to criticality. Nuclear explosives have constructive applications, such as digging canals and inland waterways, recovering valuable mineral deposits, and creating new exotic elements. The ability of the U-235 atom to fission has opened a limitless future to mankind. Like fire and electricity, this new tool must be properly controlled. through the mining and milling stages, uranium can be handled very much like any other valuable metal. Although slightly radioactive, it can be touched without the use of gloves. Some operations which involve extensive handling of uranium, however, may require the use of gloves or respirators. Following the milling operation, uranium is put through a processing step which no other metal undergoes. This process, known as gaseous diffusion, separates the U-238 atoms from the fissionable U-235 atoms. The uranium in the form of gaseous uranium hexafluoride is pumped through specially constructed porous barriers. The end product is uranium hexafluoride, highly enriched in U-235. Later, this gas will be converted to powder or to metal. Once uranium has been enriched in U-235, it must be handled in a strictly prescribed manner to prevent accidental criticality that can cause injury or death. Personnel must avoid assembling a critical mass, that is, the amount of U-235 necessary to sustain a chain reaction. This amount will differ according to the shape or geometry of the U-235, in addition to certain other factors. When criticality occurs, gamma radiation and neutrons are emitted which can cause injuries to personnel, ranging from flesh burns to the damage of internal organs. Although such accidents are extremely rare, they can occur if safety rules are not followed. These rules are derived from experiments with uranium assemblies conducted in special criticality laboratories. Data obtained in experiments assist in determining the safety limits for handling or storing certain enrichments, quantities, or shapes of uranium. Such information is used by nuclear safety engineers to make the practical decisions regarding the moving or storing of enriched uranium within a nuclear plant. Although rules and procedures may vary slightly at different installations, certain basic principles of nuclear safety are always valid. The first principle, awareness of the degree of enrichment, the percentage of U-235 contained in any unit of uranium. The higher the percentage of U-235 within any batch of uranium, the lower the quantity of uranium that may be safely placed within a given space. For instance, uranium enriched to only 2% U-235 would not reach the danger stage until it filled a drum. On the other hand, uranium with a 50% enrichment of U-235 under optimum conditions could reach the critical stage with only 2 cups of material. At a 90% enrichment, under optimum conditions, only 1 cup of U-235 would be required for criticality. The second principle for nuclear safety is the control of the quantity or mass of enriched uranium within a given space. This control is subject to such factors as the volume and shape of containers, the concentration of U-235 in mixed materials, and interaction. Since handling large quantities of U-235 increases the risk of accidental criticality, quantity can be controlled in some operations by the use of small volume containers. But if certain operations require the movement or storage of large quantities of U-235, criticality can be avoided by the use of special shapes. In the thin container, the uranium is spread out. Neutrons are more likely to escape the boundaries of the containers without coming into contact with U-235 atoms. In the fat container, the U-235 atoms are masked thereby increasing the chance that neutrons within the mass will be trapped and set off a chain reaction. These unusual-looking containers are used for storage of various solutions of U-235. Their small diameter makes them nuclear safe. These pipes contain many gallons of solutions rich in U-235, but their shape prevents the U-235 from assembling a critical mass. When U-235 is mixed with other materials, the concentration of U-235 becomes important in maintaining criticality control. Very often, U-235 in a mixture with other materials is potentially more dangerous than U-235 in pure concentration. The reason is that some materials, such as water or the various forms of carbon, tend to slow or moderate the speed of neutrons. When neutrons are moving at slower speeds, they are more readily trapped by U-235 atoms, a situation which can lead to criticality. If U-235 is mixed with a material which tends to moderate neutrons, there is usually an optimum concentration point at which criticality is most likely to occur, while below or above this point, criticality would be less likely to occur. Personnel handling enriched uranium must always be aware of the possibility of interaction. Interaction can occur when neutrons escaping from one batch of uranium cause fissions in a neighboring batch. This can be avoided by allowing sufficient distance between individual containers of uranium to allow neutrons to escape. The birdcage container is designed and constructed to provide sufficient spacing between uranium masses. But even the birdcage spacing system has its limitations. Containers should never be stacked above the height limit designated for each storage area. Proper distances between authorized storage areas also will prevent interaction. Proper spacing on vehicles, elevators, and transport dollies must be observed to prevent criticality caused by interaction. Another important principle is the control of neutron reflection. When neutrons escape from a fissioned atom, they tend to bounce about until their energy is spent and they are captured by other atoms. Certain materials placed near a mass of U-235 tend to act as neutron reflectors, which bounce the neutrons back into the U-235 mass and cause more fissions. A wall, a ceiling, a drum of water, or even persons can reflect neutrons. When a reflecting material is present, less U-235 is required to cause criticality. A final principle for criticality control is the use of neutron absorbers. Neutron absorbers are materials which remove neutrons from circulation and prevent them from causing further fissions. Elements such as boron and cadmium are effective neutron absorbers and may be used to prevent or to stop criticality. Again, the nuclear safety principles: awareness of degree of enrichment, control of mass or quantity through the control of volume, shape, concentration, and interaction, control of neutron reflection, and use of neutron absorbers. These metal buttons, highly enriched in U-235, are about to begin a typical production cycle. They are stored in properly spaced trays to prevent the assembly of a critical mass. When enriched uranium is being moved within a building, it is transported over an approved route. When U-235 is moved by truck, load limits are strictly observed to prevent assembly of a critical mass. If the U-235 is being transported from one building to another within a plant, the driver goes directly to his destination without stopping or parking en route. The U-235 should never be stored at a dock, but should be taken directly to an authorized holding area. When enriched uranium metal is machined, special care is taken to prevent the loss of valuable chips and shavings and to prevent the assembly of a critical mass. The chips remain in containers on a special rack at the workstation until they are collected and emptied into a nuclear-safe container half filled with the neutron absorber perchlorethylene. Eventually, these chips will be moved to another location for cleaning and returned to the production cycle. During the dimensional inspection of enriched uranium components, only one component at a time is permitted on an inspection table. The next component to be inspected waits its turn in an authorized holding area. In some inspection areas where other types of metals share the inspection equipment with enriched uranium, special provisions are required to prevent possible misidentification. In the radiography room, safe loading procedure is used to prevent a critical mass from forming. U-235 components are always well separated. In a typical packaging operation, U-235 components are wrapped in plastic, placed in a can which then is sealed, and loaded into a foam glass shipping container approved for interstate transport. Throughout a production cycle, many types of U-235 waste products are generated. These chips and shavings are cleaned and briquetted for re-entry into the production system. Mop water, filters, and combustibles all contain tiny but nonetheless valuable quantities of U-235. Solutions from this and other liquid salvage operations are stored in nuclear-safe containers. Eventually, these solutions will be fed into a central uranium recovery system consisting of extraction columns. After passing through the columns, the uranium is evaporated and converted to uranium trioxide, then to uranium tetrafluoride and re-entry into a production cycle. In all production and recovery areas, gamma radiation detection systems are installed for the protection of personnel. If the radiation level should rise because of an accidental criticality, an alarm system is activated. In an emergency, personnel would evacuate a building by well-marked routes and regroup at designated assembly points. If radiation contamination is suspected, persons are monitored by health physicists. Other post-accident aids for determining extent of radiation levels include special materials inside the personnel identification badges and dosimeters located in work areas. In some installations, criticality control is made more complex because of the presence of uranium-233, a uranium isotope produced in a nuclear reactor. U-233 requires stricter handling procedures than U-235 because less U-233 is required for criticality and because it is often associated with highly radioactive products. Some installations handle plutonium, also a nuclear reactor product. Plutonium is more highly fissionable than either U-235 or U-233 and has a high alpha radiation activity that requires special facilities for handling. The handling of fissionable materials such as U-235, U-233, and the isotopes of plutonium requires a constant alertness on the part of personnel to prevent criticality accidents. Workmen in the enriched uranium processing industry have established an enviable safety record by adhering to established rules for nuclear safety. As the need for nuclear power continues to grow, and as national defense commitments continue, more and more enriched uranium will be processed in production plants. It is the responsibility of every person employed in the processing and fabrication of enriched uranium to prevent the waste of this valuable resource and to maintain the excellent nuclear safety record.